And therefore, a terminal voltage stabilization system has to be added to it, and that is very important aspect, right? Now, that terminal stabilization system or voltage stabilization system depends on what are the inputs and what are the output parameters of the whole system. And now they are explained here. Let us see what are the things involved and where the error could come in. See, for example, we are using as first is voltage generation, and that generation is coming because we are charging the capacitance, and capacitor, we are charging the capacitor, and capacitor is formed because of this high voltage terminal and the pressure vessel. So it's represented by C here. Then there are various currents. For example, the charging current, which is flowing, so I call it I charging here, and that is coming in. So the voltage is developed because of that. But what are the other loads which the charging current has to match? And you can see various loads are that there is a corona, there is a column current which is responsible for voltage gradient. Then there is because you are after charging, there will be some leakages in the accelerating tubes, and always some current will flow through that. So we call it I tube, and then we are accelerating the beam, and that also has to be taken in. So this IC or I charging has to at least match with this. And then for corona stabilization system, this is a corona stabilization system here, and it's basically a triode, which I will explain later. But here what is happening is between high voltage and this, there is a COM sort of thing, and there is a constant amount of current is flowing here because of corona formation. So we try to modulate this by the feedback system. So that is how it is. But this is a sort of constant corona load all the time because of this. So these are some of the loads and which have to be taken into account. Now, how the voltage is done, how the voltage stabilization is done. One is that we use corona probe, and other one is using the GVM itself. So let's say that this is a system which takes care of this procedure. So either you can use one of them. So this is coming because of feedback, and either the input to this corona stabilization system is either from the feedback of the slits, which is coming from the energy, or it can be from the GVM itself. So you can see that. So this is one circuit of corona stabilization system or voltage stabilization system, which is used in the 6 million volt tandem accelerator at BRC. This we call it folded tandem ion accelerator here. Now V is equal to Q by C is the basic formula which we all remember. And this is also shown that V, the voltage, will depend on I belt, which we are supplying, and current, which you are drawing through this, and the corona stabilization. So corona stabilization, basically we modulate this because beam is more or less fixed, and I belt has to take care, belt or the pellet chain has to take care of this. So what we do is that we modulate I corona over the corona systems here, and that is used for corona stabilization units. Voltage is stabilized because you can see here that suppose you take this Venn diagram, and in Venn diagram this is the charging system here, where I belt is used for charging the high voltage terminal, and this is the accelerating tube. You can see this is the accelerating tube, and this is a resistor chain which is establish the voltage gradient here, and this is the this is a corona stabilization system, which is basically nothing but the triode, and it's shown here. You can see this is the corona stabilization triode system. How it works, let me explain it. In any triode system, you know that the load or the current flowing from anode to cathode here depends on how much is the voltage on a screen, and normally screen is negatively charged, negative voltage is applied. Now, so what we do is that we modulate this screen voltage with respect to anode and cathode from the beam which is falling on the feedback slits here, you can see. So what happens, let's say if the screen is more negative, then of course the current passing, let's say the current going from anode to cathode will reduce. So if it becomes more negative, it will become less current will pass through this, and if it becomes less negative, the more current will pass. Less negative, more current will pass, and when the more current is passing, the voltage will come down, will go down. And if it is a current is reduced, less current, then it will go up. So this is how it takes place, and you can see here how it is happening. So in accelerator, the beam is accelerated, and this is analyzed for the energy. Now, magnetic field is set up in this magnet. This is called analyzing magnet, corresponding to a particular energy, and that energy depends on the voltage. So if there is a variation in the voltage, the energy will change. So let us suppose that voltage V0 is the correct voltage, and if there are two possibilities here, following things can happen. Voltage V increases by delta V. That means ideally we have set up at V0, so V, which is actual voltage, has become V0 plus delta V. So once the voltage has increased, the energy, beam energy, will also increase, or it will be higher. Once it is higher, then for a fixed magnetic field, deflection will be less here, and therefore more beam will fall on B. You can see this, we call it high energy. Now the energy has increased, so this we call it high energy slip. So the more beam will come, and since beam is always diverging, so some beam is always falling on both of them, A and B, but here now because of increase in the energy, more beam will fall on B. So if you convert this current or the charge into voltage and take the difference, that means VB minus VA, then you will see that if it is falling, the energy has increased here, that means VB minus VA will be positive. And when you add this positive, this becomes less negative. And when it becomes less negative, means more current will pass through. And when the more current is passing through, the voltage will come down. Now that is what we wanted, because the voltage has increased. We wanted to bring it down. And that is what is happening. So for a fixed magnetic field, deflection will be less, and hence beam will fall on slit B, we call it high energy slit. The charge is converted into voltage through some circuit here, because is the charge collected on this. The voltage difference V minus A, as I explained this, is will be positive now. This is added to the screen voltage, which is this voltage, which is at negative potential. So when the positive you are added to it becomes less negative now, and as a consequence of that, the current will more current will flow from anode to cathode. That means it is a more load in the triode circuit, and the voltage will come down or decrease to V value. You can adjust the parameters in such a way that it exactly matches and the voltage will come down and it will become V naught again. And that is what we wanted. So this is called voltage stabilization. So this is one situation when the voltage has increased. Now suppose the voltage had decreased. That means it has become V naught minus delta V. What will happen? Now the voltage has decreased and therefore energy will be lower. This energy is lower. So energy is lower. For a same magnetic field, there will be more deflection, and therefore more deflection means the more beam will fall on this slit A, which we call it at low energy because they say low energy slit. So more beam falls on A. So if you take that again the difference, that means voltage, we can say VB minus VA, or we call it VAV, then it will be negative now because it is falling on this. We are taking B minus V. So it will be negative. So when you add this negative to the negative, it will be more negative. It will be more negative. And screen will be more negative, means less current will flow through the circuit. That means this circuit. And less current will flow, less. So load is, you are decreasing the load. And this will amount to voltage will go up. Now load has reduced, so voltage will go up. And that is what you want. So this is nothing but the voltage stabilization. So this is how the voltage stabilization takes place using, this is one of the method. Other method is, as I said, that even the generating voltmeter itself can also be used. So what you can, the same procedure will be same. So what is happening there, that generating voltmeter has measured, let's say, voltage V naught, and if slightly increases, then you again measure it. It has become V naught plus delta V. Or when it decreases, it becomes V naught minus V delta. So then this can again give a feedback in the generating voltmeter itself. And that also can be used in the similar, the arguments are same. And therefore it can also be used for voltage stabilization. So you can see that this circuit here, what you are seeing here, this circuit is using the voltage stabilization using the feedback from the slits, and that you call it slit mode. You can use slit mode. Other one is that you can have the correction or the feedback from the generating voltmeter itself. So you compare the voltages, actual voltage with the reference voltage, which is V naught, and then give the feedback to this system. So this is given here, and when you do it, it basically modulates the corona current here in this region, and that increases or decreases the load. This circuit was designed by M.J. Kansara, Sapna Padam Kumar and colleagues of IITs BRC. It worked very well, and we could achieve in both the cases the voltage stabilization of about 2 keV at highest voltage of 6 million volts. So this circuit worked very well. So, to summarize the whole thing is that although initially this GBM measurements were used to get an idea about the voltage value, particularly to avoid the corona discharges. But later on, with the advancement in the technologies, even with the GBMs, voltage stabilization is also done nicely, as well as the voltage measurements have also been done accurately. Now, in this one of the contribution in the error will come due to resistor values, and therefore we have to use high quality resistors. And if we use that high quality resistors and take care of other things, the voltage stabilities of 10 power minus 4, less than 10 power minus 4 can be achieved. Delta V by V of less than 10 power minus 4 can be achieved and have been achieved. And this is equivalent to 1 keV in 10 million volts, which is a very good. However, we still, if you want to go to even better measurements, then we have to measure or determine the energy, not based on this, but based on more accurate methods, which are based on the magnetic field value calibrations using the nuclear reactions. And nuclear reactions of two types have been used for calibration, and one is resonance type. They are very accurate values they give, or other one is the neutron threshold value. These experiments have been used and they give the most accurate values. Thank you very much.